This lesson is for Chapter 2, Section 2 on functions. So if everybody would get their notebooks out and open to a new section, we will get started. Textbook page should be on 173. So a function from set A to set B means that each element in A is assigned to exactly one element in B. When graphed, we can notice that any vertical line drawn through the graph will intersect the graph in only one place. You might remember talk of the vertical line test in the past, and that's exactly what it is. If it's a true function, you can draw any vertical line through the picture and it's going to cross through your graph in just one place. If it ends up intersecting it twice, you no longer are looking at a function. Each xy pair for a function represents one input, which is the x value of the point, and its output value y. It's okay for two different elements in set A to go to the same element in set B. Okay? It's just one element of A can't go to two different pieces in B. Testing for a function can be done in four ways: verbally, numerically by making a table of values, graphically by drawing it out, and algebraically with an equation. Turn to the bottom of page 174 now. We're going to look at problems A and B in that section at the very bottom. Determine whether the relation represents y as a function of x. Now, the domain is given to us here as -2, -1, 0, 1, and 2. And the range is as such, 3, 4, and 5. Now, -2 goes to 3, -1 goes to 1 and 4, 0 goes to 4, 1 goes to 5, and 2 goes to 5. Now, this does not represent a function. And only because of one fact. You have one input, -1, that results in two separate outputs. That's not okay. So if you were a little fuzzy on some of that wording of those slides previous to this, this is what that was referring to. Okay, it's not a problem at all, for example, that both -2 and -1 end up resulting in a 3. That's not a problem. But you can't have a single input turning into two separate outputs. No function. Letter B gives us a table where inputs and outputs are listed. So take a look with all the different inputs there, not any of which go to two separate numbers in the output line. Letter B does result in a function. Okay, so hopefully you're following along in the book there so you know what I was just talking about. I just don't feel like drawing that up on the slide. You have probably in the past heard the phrase y is a function of x. That means that you have an independent variable x and a dependent variable y. Y will depend on the value you put in for x. Okay? The domain, that's a word again that should sound familiar. The domain is all of the values that you have for x, and the range is all of the values that you solve to get for y. Okay, so you've got domain and you have range. They go along with input and output. Okay, domains are your inputs, ranges mean your outputs. If we're going to do the testing algebraically for a function, read the first bullet along with me here. It says if you can solve an equation for y and then conclude that each x value has one unique answer, y is a function of x. All right, so that goes very much along with that previous statement that was on one of those earlier slides. If you solve and find that y is equal to plus or minus some value of x, then this is not the case because the positive value of x and the negative value of x lead you to that same y. Okay, so that's again what would make that not a function. Look on page 175. Which of the equations shown here represent y as a function of x? Okay, so again, if we can solve for y and have unique values of x that get us there, we're okay. So take a look at this first one. If we solve for y, we'd have y squared equals negative x squared plus 8. And then to get y alone, we would have to take the square root of both sides. So y is going to equal plus or minus the square root of negative x squared plus 8. Now, because of this, there's going to be a positive and negative value of some x that gives us that same y value out front here. So not a function. This is what we can't find if we're looking to prove that something is a function. So move over to B and do the same kind of thing. Move the 4x squared over to the other side. Now, if you put a number in for x, there is only one result that you're going to get for y from it. Okay, if I put a 1 in for x every single time, I'm going to get 40 as an output every single time. If I put 2 in for x, then I'm going to get 52 every single time. Okay, so that function or that value will not change for a given value of x that I put in. When we know that y is a function of x, it's common to name the function f of x. Again, that's something I think that should sound pretty familiar. That is read as the value of f at x, or the value of the function at x, and you will often see f of x at the beginning of a function equation instead of the y. So f of x and y are fairly interchangeable. Okay, so don't let that notation bother you. F of x stands for the function value when x is put in, and when we put a value in for x, we're solving for y. So you're just looking for another way of naming y. When asked to find the value for something like f of 3, you are being asked to plug 3 into the function wherever you see an x, and then solve for the output value. So take a look at this one, page 176 in the middle. Let the function be f of x equals 10 minus 3x squared. Find each function value. So letter A gives us f of 2. So if we're going to find f of 2, it says put 2 in for any x's that you see. And that one gives us a value of negative 2. Okay, letter B, same function, but we're going to find f of negative 4. Plug in negative 4 where you see x this time. And we get a value of negative 38. Next, piecewise defined functions. Now it's going to be easier if you look at these while I'm talking about them. So let's make sure that everybody is at the bottom of page 176 now. It says a piecewise defined function is a function defined by 2 or more equations. So look at the example that they have there. They have f of x is equal to x squared plus 1 if the x values being inputted are under 0 or negative. F of x is equal to x minus 1 if your inputs or your x values are greater than or equal to 0. Okay, so depending on the number you're putting in, it's going to determine which of those two functions you plug it into. All right, so let's take a look at that one at the bottom of the page. It says evaluate the function given in example 4 when x is equal to negative 2, 2, and 3. Okay, so the functions they give us x squared plus 1 if x is less than 0, and x minus 1 if x is greater than or equal to 0. So if we're going to solve for negative 2, so if we're going to do f of negative 2, which of those two functions would we be using? It would be the top one because that's a value less than 0. So negative 2 squared plus 1 would be a 4 plus 1 or 5. Okay, the second value that we're supposed to do is f of 2. Now that input is a positive number, so we're going to use the bottom equation, or bottom function, excuse me. And we get a value of 1. And the third one, we'll do that one yet here real quick, a value of f of 3. Again, using that second function because, again, we are greater than or equal to 0. And we get 2 for our output. Finding values for which f of x is equal to 0. This is very much the same as finding your x-intercepts, because remember, f of x is another way of saying y. If y is equal to 0, we're going to end up with the value for x that would place that point on the x-axis. Okay, so put 0 in for f of x and solve for x. Very much like finding y-intercepts. Take a look on page 177 down in the middle. Find all real values of x such that f of x is 0, where f of x is equal to x squared minus 16. Okay, well, if f of x is 0, or we're looking for where it's 0, that other side there, that x squared minus 16, factors. So where would f of x end up equaling 0? Where x is going to equal 4 on this one, and negative 4 on the second one. Okay, so that's similar to some stuff we've been looking at relatively recently. Next thing, okay, if you look down midway part of the page, example number 6 in your textbook, finding values for which f of x is equal to g of x. So if they give you two functions, an f function and a g function, and they want them to be equal, take the two functions and set them equal to each other and just solve what you see. All right, so at the very bottom of the page, I pulled that one to do because the other ones are already done for you in the book. So if we're going to find f of x is equal to g of x, we're given this function for f of x, and this one for g of x. Okay, hopefully everybody can see that at the bottom there. So if we're looking for values where they're equal to each other, take them and set them equal to each other. So here's the f of x, put it equal to the g of x, and now we solve. Now notice that both functions had an x squared term in them, but one was negative while the other one was positive, so get everything over to the left-hand side. They're not going to cancel out for us. So if we add x squared to both sides, we now have 2x squared. If we subtract 4x from both sides, we have a positive 2x, and then minus 24. Notice that every term of that equation or that expression on the left-hand side can be factored by 2, so pull that out. Now you're looking at a trinomial that can be factored more. So the x's that we could use that would end up making f of x and g of x equal would be negative 4, we can see from this part, and positive 3 from the second part. All right, turning to page 177 at the, oh, I gave myself a slide for that, sorry. I guess I wrote it on the previous page. So we get to skip to the domain of a function, next page. Now, domain, remember we talked about that word already. Domain is the set of all real numbers for which the expression is defined. They are all of the x values that can be put into your function. Couple things to consider. Denominators cannot be 0, for example. Square roots, radicals, cannot have negative values underneath. These are all things to consider when you're trying to decide what can be in a domain or not. Okay, so the domain is consisting of all x values given in the ordered pairs of a function. Domain goes with x values. So let's take a look at these couple of examples. They're printed in your textbook on the bottom of page 178. For letter A, find the domain of each. All right, so the domain are the inputs. What are your inputs? In the first point, -2. Second point, our input or our x is -1. And then 0, 1, and 2. Okay, letter B, g of x is equal to 1 over 3 minus x. There aren't many things that are not going to work in this domain, but remember we cannot allow that denominator to end up at 0. So your domain here is going to be all real numbers x except x cannot equal 3. Okay, letter C gave us the circumference formula. Now something to ponder here. If we're looking for things that can't work here, or things that could not be plugged in for R stands for a radius. If it's a radius, you cannot have negative or 0 radiuses, or you wouldn't have a circle. Okay, so the domain here is going to be all things where R is greater than 0. The last one at the bottom is one that does have a radical in it. So to give us a look at one of them as well, we know we cannot let that amount underneath our square root sign be negative. Those are imaginary. So x at the very least has to be 16 or higher. Okay? Anything less than that's going to end up with a negative square root. All right, these application problems starting on page 179. The first one here, they do a little bit with that iced tea can in the done out examples for you in the book. We're going to look at them some more because this isn't such a bad thing to put your head around. It gives us some information on that picture there. For example, there's a ratio of height to radius of that can. The ratio of the height to the radius is 4. Everybody see that on top of the can there? We're going to need that information. You guys all know what a radius is. It's halfway across the can, half of the diameter, and then you've got the height of the can. So if we're talking volume or surface area, all of those bits of information are going to be needed in order to calculate those two concepts. So the book does volume for us. We're going to take a look at surface area. Now, surface area formula, they don't give here, but it's this. The total surface area of that can is going to be the lateral area, which is the 2 pi r h. If you would flatten that can out, the wraparound piece is going to be a big rectangle. 2 pi r is the length of it, and height is going to be the width of it. That part of the formula covers the rectangle piece. 2 pi r squared, of course, is going to be the two circles that are the top and the bottom of the can. We're going to try to solve first as a function of the radius. So in other words, we don't want any h's in there. We wanted a function of the radius. So look at that ratio that they gave us. R is equal to h over 4. Okay. We also can rewrite that. You know, if you'd multiply both sides of that ratio by 4, do you see how we could convert that to say 4r is equal to h? Now we have something that we can plug in and substitute every time we find an h in our formula. We can get rid of all the h's. So go now back to the formula and do that. And simplify. do that, notice both of the terms here have a pi in it and an r squared in it, so we can go ahead and combine them. 8 and 2 make 10 pi r squared. So that's the first one. We got it to be rewritten as a function of r, no h's left. Now we're going to do it the other way, and we're going to write it as a function of h. So that means now we want to get rid of the r's. So r is equal to, come back to that ratio, r is equal to h over 4. So put that in every time you see an r. Okay, so all I did was plug in the h over 4's for those two r spots that are in the formula. Now start simplifying. Okay, so by reducing and simplifying, I'm to this point right here, and now I'm looking at two fractions that I want to combine. What do you need to have to combine your fractions? You have to have a common denominator. Guess I only multiply by 4 there. Get it over 8. Then putting these two together, we have 4 pi r squared, or 4 pi h squared plus pi h squared, which is 5 pi h squared over 8. So there's the function in terms of h. Next one, the path of the baseball. Again, there's one there for you to look at from the book. We're going to do the one at the very bottom of the page, and I was not going to retype that whole thing. We're looking at a second baseman throwing a baseball toward the first baseman that's 60 feet away. The path of the baseball is given by that function that's written there. Okay, so here's the function. Now, in the problem, it explains to us that f of x stands for the height of the baseball. Okay, and it explains to us that x is the horizontal distance that you're working with. So now go back to the story problem. Let's find this information. So the second baseman throws a baseball toward the first baseman 60 feet away. There's your horizontal distance. The path of the baseball is given by blah, 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 where f of x is the height of the ball in feet, x is the horizontal distance from the second baseman in feet. The first baseman can reach 8 feet high. All right, so he can get 8 feet in the air to catch this ball. Can the first baseman catch it without jumping? All right, so if we're looking at a height with a distance of 60, we're trying to solve for f of 60 feet. All right, simplify. Plug all that into your calculator. You're going to get negative 14.4 here, and then positive 18 here, and 6, and all of that's going to come together to 9.6 feet. So the height of that baseball, if it's chucked with that formula, 60 feet is going to be 9.6 feet in the air. And so if this person can only reach up 8 feet, they are going to miss that ball. No catch. Now, here's the last one that we're going to take a look at today. The difference quotient is a problem where you're going to be given a function and then asked to play or manipulate that function. And it's kind of calculus related, but it's not a bad thing. It's very much just a substitution piece. If our function f of x is x squared minus 4x plus 7, we can find f of x plus h. And all that means is every time you see an x in the function, f of x plus h means you're going to plug x plus h in instead of just the x. All right, so watch, and I think it'll make more sense. So that first piece, we're going to take f of x plus h. So x plus h squared, plug it in for the first x, minus 4, plug x plus h in for the second x, plus 7, and now we want to subtract, I think I'm going to keep that together. Now we're going to subtract just the regular f of x, which was the given thing. And then our problem, or our quotient, says to put that whole thing over h. So all I've done right now is fill that thing in. Okay, now you begin to simplify. Remember that x plus h squared is an x plus h times another x plus h. You have to FOIL. So we're going to get x squared plus 2xh plus h squared. Distribute your negative 4. So that's the first part. And then minus the second. All over h. All right, so simplifying. That subtraction piece on the back end, I'm just going to rewrite minus x squared. Subtracting a negative 4x is plus 4x, and then subtract 7. And I'm going to rewrite it like this so I can start combining like terms. All right, so my first chunk has a positive x squared. My back chunk has a negative x squared, so they're going to go. My first chunk has a negative 4x. My second has a positive 4x. They're going to go. And I have a positive 7 and a negative 7. So all of those things are going to cross out. All that's left then is what I've just written. We had a 2xh, we have an h squared yet, and we have the negative 4h that we haven't done anything with. And the h on the bottom we haven't done anything with. Now look at all of your terms on top. Each of them have an h. Pull it out, factor it out. We'll be left with 2x plus a single h minus 4 all over that h on the bottom. Now you can reduce. Top h, bottom h cancel. 2x plus h minus 4 is our end result. All right. I think I've talked long enough. Now, your assignment starts on page 182. Again, do several of each section and go heavy on the word problems. I am going to collect a few tomorrow. So on a separate sheet of paper, I want you to work out specifically number 6, 22, 34, 46, and 56. Okay, so give those 5 a try on a sheet of loose leaf or notebook paper that you're going to turn into me when you get to class tomorrow morning, or not tomorrow morning, tomorrow afternoon. Okay, come in for help if you want. I'll see you guys tomorrow.